Swayam Prabha. Digital India. Educated India.
Till now we have done hydrogen production. From this section we will start hydrogen storage. Whether hydrogen is produced in a centralized plant on an industrial scale or whether it is produced on a small scale in a decentralized plant, it is not essential that the requirement can be in pace with the amount of hydrogen being produced. Except for some of the applications where whatever hydrogen is being produced is being utilized, most of the time in order to bridge the supply demand gap, hydrogen storage is essential. Now hydrogen storage is the important part of the hydrogen value chain and it is the biggest bottleneck as well. Let us understand what are the challenges associated with the hydrogen storage. On a mass basis, hydrogen has advantage. Its energy density on a mass basis is high, like in 1 kg it is 120 megajoule of energy which is stored in hydrogen, which is more than double that of methane. For methane it is 50 megajoule per kg, for LPG it is 46 megajoule per kg, for gasoline it is 44 megajoule per kg. These are on the lower heating value. On higher heating terms, hydrogen energy density is 142 megajoule per kg. For methane it is 55.6 megajoule per kg, LPG 50 megajoule per kg, gasoline 47 and diesel 45 megajoule per kg. So, we can clearly see that hydrogen has a much higher energy density, almost 3 times that of the gasoline, more than double that of the methane. But the entire picture changes when we consider on the volume basis. Now hydrogen, it is the smallest molecule, it is the lightest molecule, it has a very high diffusivity, all that poses a lot of problem when it comes to storage. Now under normal temperature pressure conditions, the density of hydrogen is 0.089 kg per meter cube. So that means in order to store 1 kg of hydrogen we will require 11 meter cube of volume, and that is an enormous volume. The energy that will be stored in 1 liter is only 0.01 megajoule, which is very less as compared to that of gasoline. For gasoline, on a volume basis the energy density is 32 megajoule per liter. So, this is roughly 3200 times higher than the energy stored per liter in hydrogen under normal temperature pressure condition, while it is 3600 times higher for diesel. It is 36 megajoule per liter of diesel. Now that means in order to store substantial amount of hydrogen in a given volume, we need to either compress it to a higher pressure or make it more dense by liquefying it, or we have to see some other ways in which it can be stored in the solid form. Now in order to increase the density, in order to increase the volumetric energy density, we can compress it to higher pressure. Like if hydrogen is compressed to say 200 bar, the energy density becomes 1.8 megajoule per liter and the density of hydrogen 15 kg per meter cube. If it is compressed to 350 bar, then it is 2.84 megajoule per liter and the density of hydrogen becomes on compression to 350 bar 23.65 kg per meter cube. To very high pressures like 700 bar, then the density further improves to 4.82 megajoule per liter. So, it is 40.2 kg per meter cube. This is still half of, even at such high pressures of 700 bar, this is half of that of methane when it is stored at 200 bar, which is 8.39 megajoule per liter. However, if we further compress methane at 700 bar, it is 15.8 megajoule per liter, and which we can see that this is 4 times that of the hydrogen being stored at the similar pressure. Now, the other way could be, we could further increase the density by liquefying it. So, the liquid hydrogen when considered at 1 bar pressure, its density is 8.5 megajoule per liter and it is 70.9 kg per meter cube of hydrogen being stored. This density can be further increased if it is stored in the solid state form. Then it goes to like higher than 100 kg per meter cube. So, this is the biggest challenge, that on energy basis hydrogen has a very high gravimetric energy density, but on a volume basis it is very low. So, there are challenges associated with the conformable storage of hydrogen in a given volume. So, the weight as well as volume required for storing hydrogen becomes a challenge when especially it is up to vehicular application. Other than that, the other challenges that need to be considered when storing hydrogen include its cost of both the material as well as the tank, durability, operability. So, it should have very high life, at the same time the operating conditions should be optimum. It should have a high charge and discharge rate. So, rate at which hydrogen can be put inside the tank and the rate at which the hydrogen can be taken out of the tank, either system or materials as well. So, at which it gets charged in a solid state material or it gets discharged. Refilling time is another consideration when it is to be compared with IC engine based vehicles. It should be of the similar order as that of a IC engine vehicle. Duration of storage. Now, this becomes important when it is liquid state storage. There should not be loss of hydrogen when it is being stored. So, the dormancy becomes a major parameter there. It should be very fast in response, like when the hydrogen storage system is connected to fuel cell or a load, whatever are the changes taking place in the load, then it should respond faster. So, the delay should be as low as possible, as well as the transient response need to be considered. The fuel quality, so there should not be any contaminants or impurities present that should come from the either the compression or from the tank, which could be detrimental to its integration towards its integration to the fuel cell. Efficiency is important, whether it is we have to compress it, whether we have to liquefy it, so as to make it more energy compact. Safety of the storage devices are important, the conformability, weight and volume. These are other parameters that needs to be considered when we have to store hydrogen. Now, just taking an example, roughly 1 kg of hydrogen, a light motor vehicle, we can drive about 100 kilometers. So, in order to have a range of 500 kilometers, 5 kg of hydrogen need to be stored in a hydrogen container, vessel or tank. Now, if equivalent amount of energy which is stored in 5 kg of hydrogen could have come from gasoline, the volume of the tank would have been 49 liters. The similar energy, if to be stored in the form of hydrogen under normal temperature and pressure condition, would require 11,940 liters of volume, and that is very high as against that of the gasoline tank. Now, if this is further compressed, hydrogen is compressed to say 300 bar, then the volume of the tank would reduce to 212 liters, If further compressed to 700 bars, this tank volume would reduce to 125 liters. When it is stored at a even further higher pressure, say 850 bar, then the tank volume required would be 111 liters. When it is liquefied, hydrogen is in the liquefied form in a cryogenic tank, the volume required to store the same amount of hydrogen, 5 kg of hydrogen would be required will be 75 liters. But if it is stored in the solid state form, the volume required will be 33.3 liters. So, this is how the different ways of storing hydrogen are related as against the gasoline tank. Looking back into the history of hydrogen storage, it was used for various applications and was stored as early as 1880s in wrought iron tanks. However, the pressure was lower at that time. After that, steel tanks were introduced wherein the pressure was increased to 120 bar, but these tanks were very heavy and the weight of the tanks was about 500 kg. Thereafter, there was increment in the pressure in 1960s. The pressure which was increased was to 150 bar, and after 1960s it was even further raised to 200 bar, and primarily these were used for space and military application. It was in 1980s that the pressure was increased to about 300 bar, but at that time like these were used for leisure applications like paintball, for diving, for storing various gases. Thereafter it has seen a great improvement in terms of increase in the pressure and decrease in weight. So, we will see the different types of tank and we will see how the type 4 tank, they have a lower weight and a increased pressure. Before coming to the hydrogen storage techniques, we will first quickly look at what are the important properties which we need to revise before we go on to a particular method of storage. Let us start with the phase diagram. We know that under normal temperature pressure condition, hydrogen is a gas with a very low density. Now there are different lines in the phase diagram which separates the different regions, which separate solid from gas, which separate gas from liquid, from gas from solid. So these are the equilibrium lines which separate the different regions in the phase diagram. Now as we lower down the temperature, at a temperature of minus 253 degree centigrade 20 K, liquid hydrogen is obtained. So this region is that of liquid hydrogen, a very small region. Now all the three phases, solid, liquid and gas phase, they exist at this point which is known as the triple point. It has a temperature of 13.96 Kelvin and a pressure of 7.36 Kelvin. At a critical point which has a temperature of 33.15 Kelvin and pressure of 1.3 megapascal, here the gas and the liquid phases are indistinguishable, and beyond that even if we further increase the pressure we cannot liquefy hydrogen. So this is where we can get liquid hydrogen, this is corresponding to the critical point. Now if it is temperature is further reduced, so if we go further down from 20 Kelvin say to 14 Kelvin or minus 259.2 degree centigrade at atmospheric pressure, we can get solid hydrogen. Now prior to that, when we reduce the temperature below 20 Kelvin, we get a state which is slush hydrogen. This is a phase wherein solid and liquid phases are indistinguishable, but this is obtained at a lower vapor pressure. So while storing this hydrogen, any air ingress need to be avoided because the vapor pressure is below the atmospheric pressure. Now what happens is beyond the critical point is the supercritical hydrogen. Now this supercritical hydrogen, it is like both the characteristic, it has a characteristic like liquid as well as gas. So it can have a flow like a liquid flows, while it can be compressed like a gas. So this is the beyond this 20 K, it has a solid region. Now this solid hydrogen, it was found that even if we keep on increasing the pressure, this solid hydrogen will exist, and it is till a pressure of 10 to power 11 Pascal or 200 Kelvin. The solid hydrogen was identified to have 4 different phases, and these 4 different phases are like HCP, hexagonal closed packing, or FCC, or orthorhombic and monoclinic. But if we further increase the pressure to beyond 8 into 10 to power 11 Pascal at a temperature of 10 to power 2 to 10 to power 3 Kelvin, we can even get metallic hydrogen. And if we go further beyond this, in that case we can get a liquid metal. This liquid metallic phase was identified way back in 1935, but it was observed in 1996. And this is the phase which is found in various planets like Saturn and Jupiter. At further higher temperatures 10 to power 4 to 10 to power 5 Kelvin, it can be found in plasma phase. Now this phase is found in stars, this phase is found in sun. So this is the overall like which region hydrogen can be found in which phase. Now like any pure substance, the state of a hydrogen can be described using 2 intensive state variables, and rest of the variables we can find using the different relationship which are like the equation of state, which relates the temperature, pressure, volume, the calorific equation of state which relates the internal energy, temperature, volume, and the enthalpy, temperature, volume, or there can be entropy relations like temperature, entropy, volume, and temperature, entropy, pressure relationships. Now other state variables we can found using these 3 relations. Now at normal temperature and pressure conditions, we know that hydrogen behaves like an ideal gas, and it follows the ideal gas law, PV is equal to nRT, and this is for low pressures and high temperatures beyond the critical point. And we know that the ideal gas assumptions are like the forces between the molecules should be negligible, molecules are considered as a solid, hard spheres, incompressible spheres. But then at high pressures and low temperatures, deviations from the ideal gas behavior is observed, and that can be accounted by various models like the van der Waals equation, wherein the intermolecular forces and the molecular volume is accounted for by addition of 2 more terms, like to the pressure term plus A upon V square and V minus B is equal to RT, where A and B values for hydrogen are like 0.025 meters to the power 6 Pascal per mole square, and same for B value we can obtain. Another way to represent this deviation of hydrogen from its ideal gas behavior at a higher pressure and lower temperature is by including a dimensionless quantity, which is the compressibility factor. So we can, in its presence, we can modify the ideal gas equation as PV is equal to NZRT. So Z is here the compressibility factor, and this accounts for the deviation from the ideal gas behavior. So N ideal upon N real, or same the mass when we consider as ideal gas to the mass when we consider it as a real gas. Now any value which is away from 1 shows that it is deviation from the ideal gas behavior. So this is like as we decrease the temperature, the deviation further increases. Now let us take an example where say at 300 Kelvin, and when it is compressed, hydrogen is compressed to 300 bar, the compressibility factor is 1.2 under this condition of temperature and pressure. That means if we have considered ideal gas equation to calculate the mass of hydrogen stored in a tank, we could have overestimated the mass by 20%. Now these relationships like the compressibility factor relationship, these are available in the literature, these graphs are already there, and that can be used to see how much is the deviation from the ideal gas behavior. And now here if we find the reduced pressure like by dividing the pressure by critical pressure or dividing by the temperature by critical temperature. In that case we can get the generalized compressibility factor which is for different gases. Now when it comes to storing hydrogen in liquid form, we need to understand that the hydrogen, which is a diatomic molecule, it has two, so hydrogen atom has a proton, and the spins of the elementary particles, they can be either parallel or they can be anti-parallel. Now when we consider the equilibrium concentration or under the normal conditions, the normal hydrogen is a mixture of 75% of ortho hydrogen and 25% of para hydrogen. So this is also known as equilibrium hydrogen. Now these two states of hydrogen, ortho and para hydrogen, they have slightly different properties. Now once we start cooling from the normal temperature pressure condition to liquefy hydrogen, this ortho hydrogen has to be converted into para hydrogen, because in liquid hydrogen it is a mixture of ortho hydrogen as small as 0.179% and para hydrogen 99.821%. Now this conversion of this ortho hydrogen from room temperature to 20 K into para hydrogen, this is an exothermic process, because the para hydrogen is in a lower energy state. So when you cool it down, the extra energy is released. So this conversion is an exothermic process, releasing energy of 670 kilojoule per kg. This is even higher than the energy required for liquefaction. So the latent heat of vaporization for hydrogen is 446 kilojoule per kg. So when we are trying to liquefy hydrogen, we have to not only remove that energy, we have to provide the required conditions to liquefy it. At the same time we will have to remove this energy or the heat which is coming out because of this ortho para conversion. Also for hydrogen, the inversion temperature is 193 Kelvin, that means it has a positive Joule-Thomson coefficient above this temperature. So we have to cool it down and we have to remove that much amount of heat, extra heat which is being produced. For a positive Joule-Thomson coefficient, when we are trying to expand hydrogen, it will in fact heat. So that extra heat needs to be removed. So there are two major disadvantages because of that. We have to not only remove that extra heat, but if there is a sudden depressurization, release of pressure, then a large amount of heat can be produced and that can even lead to ignition. Actually it is not ignition, but it can lead to explosion as well. Now these are some of the important things we need to know before we look at the different hydrogen storage methods. When we see how we can categorize these methods, so the different hydrogen storage methods can be categorized into the way like physical storage, wherein we are storing it in the molecular form. It can be either in the form of gas being compressed to higher pressure, so compressed state storage, or hydrogen can be liquefied and stored in the liquid form, or it can be stored in the molecular form on the using the adsorption based methods on high surface area materials. Hydrogen can be stored using chemical storage method. This can be on various materials using like solid state storage. These can be either metal hydrides, complex hydrides, or in some of the chemical hydrides, or in liquid organic hydrogen carriers. So all these methods we are going to learn in more detail. Now these systems which are developed for hydrogen storage, or these materials which are going to be developed for hydrogen storage, they need to satisfy certain requirements in terms of mass basis, in terms of volume basis, cost, under what conditions they need to operate, what should be the refueling time, what should be the dormancy. All these parameters, for that US DOE has laid down certain targets in association with US Drive. So these targets are system level targets. which are considered not only for the stored mass, the fuel in the tank, but also considering all the associated auxiliary components, whether these are the tank weight or volume, whether the walls, pipings, fittings, manifold, balance of plant, cooling system, the storage media, it could be even the integration where it has to be connected to the refueling unit. So, all those auxiliary components are also considered when considering these storage target. So, these are considering that if a vehicle, these are for the onboard on a vehicle, considering that a vehicle, light duty vehicle has to be driven for 500 kilometers, and this should be at par with the IC engine vehicles. Now, these targets which are offered, these are revised after every 5 years considering the improvements in the technology. So, these are not based on the state of art the technologies, but rather these are based on what is the customer demand and what are the requirements in terms of a particular vehicle when it is being considered. So, these targets are for different storage parameters like the system gravimetric capacity. So, this always is gravimetric when it comes, then it is per unit mass which is being considered. So, this is the amount of usable energy which the system will have. So, this is the specific energy from hydrogen which can be provided to the fuel cell system. So, it is the net useful energy divided by the maximum system mass. Now, this system mass includes the mass of the hydrogen being stored as well as the mass of the tank, storage media, the walls, fittings, tubings, any cooling devices, compression related unit, filters, safety units, monitoring, sensing, all these devices are to be considered when it is being considered as a storage system. Its units are in kilowatt hour per kg. So, by 2025 it has to be 1.8 kilowatt hour per kg, and ultimate it should be 2.2 kilowatt hour per kg. In terms of kg of hydrogen stored per kg of the system weight, it is 0.055. So, that is about 5.5% weight percent of the hydrogen should be stored per kg of the system weight. Similarly, the ultimate it is 0.065. So, 6.5% of the hydrogen to be stored to the system mass. Same is expressed in terms of the volumetric capacity, that is the amount of energy which is available in the form of hydrogen to the maximum system volume. So, the net useful energy divided by the system volume, and this is expressed in kilowatt hour per liter of the system or kg of hydrogen per liter of the system. So, kg of hydrogen being stored per liter of the system. So, if we consider in unit of kilowatt hour per liter, it is 1.3 kilowatt hour per liter by 2025 and an ultimate of 1.7 kilowatt hour per liter. Similarly, 40 grams of hydrogen to be stored per liter of the system by 2025 and 50 grams of hydrogen to be stored per liter of the system as an ultimate target. Storage system cost, it is in dollars per kilowatt hour net. So, $9 per kilowatt hour and $8 per kilowatt hour as ultimate. Hydrogen, dollars per kg of hydrogen, and at the pump, so this is 300 and 266 and $4 per gasoline equivalent, gallon of gasoline equivalent at pump. Now, when whatever is the method of storage being used, whether it is compressed state or liquid state or solid state storage, the conditions of operations are important, like it should be able to operate under ambient condition, temperature conditions in degree centigrade from -40 degree to 60 degree. That means we should be able to operate in countries where it is extreme winters. So, we can still use it at a temperature of -40 degree, or extreme summers where even the temperature is considered inside the vehicle, the temperature may go as high as even 60 degree, then also we should be able to operate such systems. Minimum or maximum delivery temperature, that is when hydrogen has to be delivered to the fuel cell system. Usually PEM fuel cell is used, so which operate at close to 80 degree centigrade, but we should be able to operate it in a range of -40 degree to 85 degree centigrade. Life cycle of the storage system, from 1/4 tank to full tank, the number of cycles we should be able to get is 1500 cycle. Now this is actually considering the different, all these targets are considering a wide range of vehicles, wide range of amount, and finally these targets have been come across. Now the minimum delivery pressure from the storage system to fuel cell, so the pressure in bar, this is 5 bar 2025 as well as ultimate, and that maximum pressure from the storage system 12 bar. Onboard efficiency of the fuel cell of the hydrogen storage system 90%, well to power plant efficiency on board, off board, everything, it is 60% which is desired. The charging and discharging rate, they have importance when we consider the refilling time of the tank. So how much time it takes to fill the tank, that should be at par with the conventional gasoline based vehicles. So a system fill time which is expected to be in minutes to be 3 to 5 minutes 2025 and ultimate. Minimum full flow rate 1.6 gram, example like 1.6 grams target for 80 kilowatt rated fuel cell power. So what is desired is it should be 0.02 grams per second per kilowatt, an average flow rate 0.004, start to full time at 20 degree centigrade. This is important when we consider the starting up of vehicle. So from the start to the maximum flow rate, that should be achieved within 5 seconds of the operation, and similarly start time to full flow rate at -20 degree centigrade, maximum acceptable is 15 seconds. The transient response at operating temperature from 10% to 90%, this is important when it is considered as the starting of the vehicle. So certain amount of hydrogen will be there in the pipes and tubings, but after that it should attain, it should get the required hydrogen to be supplied to the fuel cell, so that it can achieve 90% of the required energy. So 10% to 90% the response should be achieved within 0.75 second. This is important during the starting up, and 90% to 0%, that means during the stopping up of the vehicle it should immediately stop, and that response time should be 0.75 second. The fuel quality, again when it comes to integrating with fuel cell, the quality should be very high, like the impurities which can be allowed to be there in the hydrogen flow should be at ppm's level, and this is as per the SAE J2719 standard. Dormancy, this is important when we consider the liquid state storage. So we will see in detail when we will study the liquid state storage that there are losses which are unavoidable in case of liquid hydrogen stored. So the dormancy time which is targeted is 10 days in 2025 and 14 days in ultimate target. So this is the minimum until first release from initial 95% usable capacity. If the tank is filled to 95% of its usable capacity, the number of days it will require for the first release of hydrogen from the tank due to boil off. So the boil off target maximum reduction from the initial 95% usable capacity, after 30 days it should be still 10% as target of 2025 and ultimate. Regarding the health and safety requirements, whether it is permeation or leakage, toxicity or safety, all these needs to be met by the associated standards which are already there. So these are the requirements for onboard hydrogen storage system. To summarize this part, we have seen that because of the low density, hydrogen being the lightest molecule, it also has a very high diffusivity, it is very difficult to confine hydrogen, and that causes several technical challenges, and also when we are compressing or when we are liquefying, there are economic challenges associated with it. So, there are different methods which we are going to see in more detail from the next class, and so these methods can be used for hydrogen storage. And then we have also seen today the DOE targets which has set in terms of system level targets. These are just to guide the researcher that these are the minimum requirement which the system should meet in order to be these systems to be commercialized. Thank you.